Now we can introduce any unit vector, e hat sub n, where the hat means it's a unit vector, and the e sub n means it's going to be a unit vector for any force vector in our system. And we calculate this by taking a vector and dividing it by its magnitude. Mathematically, e hat sub n is expressed as our vector per the magnitude of our vector. For example, if we have a vector a defined as 4.0, 6.0, 8.0, we can calculate the unit vector as follows. E hat n would be 4.0, 6.0, 8.0 per the magnitude of a, which is the square root of 4.0 squared plus 6.0 squared plus 8.0 squared. In our denominator, we'd have the square root of 116, which can be expressed as 10.8 once we take into account significant digits. Then our vector would be 4.0 divided by 10.8 in the x direction, 6.0 divided by 10.8 in the y direction, and 8.0 divided by 10.8 in the z direction. Taking into account two significant digits, e hat sub n would be 0.37 in the x direction, 0.56 in the y direction, and 0.74 in the z direction. The unit vector is quite helpful, for it tells us what proportion of our vector is existing in our principal directions. Furthermore, we can express our vector f by multiplying its magnitude times our unit vector, describing vector f. Our unit vector is going to be bounded between 0 and unity in our principal directions, and when we take the magnitude of our unit vector, it should be equal to unity. We'll just look at an example of this. Imagine we have a box with dimensions of 3.00 meters in the x direction, 4.00 meters in the y direction, and 3.00 meters in the z direction. And it has a force of 35.0 kilonewtons going from the origin, defined as 0, 0, 0, to the point P, which is defined as 3.00, 4.00, 3.00. And we want to construct an expression for our unit vector force. And we also want to determine our x, y, and z components of force. First, we'll calculate the magnitude of line OP, on which our force vector lies. Then we will calculate the unit vector that describes line OP. And this is the same unit vector that our force lies along, for they're existing in the same direction. For us to begin, we're going to calculate the magnitude of OP. We'd have the square root of 3.00 meters squared plus 4.00 meters squared plus 3.00 meters squared. And we find the magnitude to be 5.83 meters, considering significant digits. Then when we calculate the unit vector describing line OP, we're going to take OP, which is 3.00 meters in the x direction, 4.00 meters in the y direction, and 3.00 meters in the z direction, and divide each of these quantities by 5.83 meters. That is, in the x direction, we'd have 3.00 meters divided by 5.83 meters, which gives us a value of 0.515 in the x direction. In the y direction, we'd have 4.00 meters divided by 5.83 meters, which gives us a value of 0.686 in the y direction. And lastly, we'd have 3.00 meters divided by 5.83 meters, which gives us a value of 0.515 in the z direction. Now, for us to determine the x component of force, all we have to do is take the magnitude of our force, 35 kilonewtons, and multiply it by the x component of our unit vector that's describing line OP. In doing such, we'd have 35.0 kilonewtons times 0.515 I hat, where I hat is describing our direction. And we'd have 18.0 kilonewtons. To determine the y component of force, we're going to take the magnitude of our force, 35 kilonewtons, and multiply it by the y component of our unit vector, which is 0.686 j hat. And thus we have 24.0 kilonewtons existing in the y direction. Lastly, the z component of force is going to be the magnitude of our force, 35.0 kilonewtons, times the z component of our unit vector, which is 0.515 k hat, which gives us 18.0 kilonewtons in the z direction. To check that we've done the math correctly, we're going to take the magnitude of our force vector. That is, we're going to take the square root of the sum of our squares. That is, we're going to take the square root of f sub x squared plus f sub y squared plus f sub z squared. And we arrive at 35 kilonewtons, which indicates that we have done the math correctly.